Out of chapter 20. So in this lecture, we'll look at how to synthesize carboxylic acids. So in previous chapters, we've already seen several reactions that make carboxylic acids. For example, if you have an alkyl group on benzene, then so long as that benzylic carbon has hydrogens, if you remember, if it has a hydrogen, one hydrogen or more, then you can oxidize that carbon and all of the other carbons cleave off and you make a benzoic acid, right? Or if you have a primary alcohol, you can oxidize it to a carboxylic acid, if you remember what your reagents are. So any strong oxidizing agent, and we looked at several like KMnO4, H2CrO4, sodium dichromate, so forth. Or if it's an aldehyde, again with a strong oxidizing agent, then it will oxidize to a carboxylic acid. So bleach, for example, will oxidize it, KMnO4, Br2, chromic acid, right, sodium dichromate, any of those strong oxidizing agents. So those are from organic 2 reactions, and these next two are from organic 1. So if you remember, alkenes can be oxidized to carboxylic acids. So what your oxidizing agent is there. So if you can cleave the carbon-carbon double bond, right, by reacting that with ozone, and then you need an oxidative workup, so something like peroxide. So this one would go to a ketone because that carbon has 2 carbons attached, but since this carbon has a hydrogen attached, right, it would initially form an aldehyde, which then could be oxidized to a carboxylic acid. And if you had alkynes, similarly, if you react that with ozone and water, that would cleave the alkyne triple bond and make 2 carboxylic acids. Okay, so those are old reactions that you already know, and then we'll look at a few new reactions. So you can take a Grignard reagent, or it could be an organolithium reagent. And if you remember, in this case, that carbon is partial negative. So if you react that with CO2, and for the Grignard reagent, that carbon is partial negative. So if you react that with CO2, then this carbon is partial positive. So this carbon will react there and break one of the carbon-oxygen double bonds. And then in the next step, you do the acid workup. So OH+ would just protonate the carboxylate. Right now you have carboxylic acid. And again, it doesn't matter if it's a Grignard reagent or an organolithium reagent. Carbon's partial negative in both cases, so that would attack the partial positive carbon of CO2. Okay, so if you did this sequence of reactions, if you remember how to make Grignard reagents, you take an alkyl halide and react it with magnesium, typically dissolved in ether. So magnesium, insert between the carbon-halogen bond, and then now that carbon's partial negative, so that would react with CO2. So that carbon goes here, break that. And that would be your product. So if you notice in this case, if you react it with CO2, you extend the carbon chain by 1. Okay, so you can also make them from nitriles. So if you take a nitrile and acid hydrolysis, so you react it with acid and water, and you typically have to heat it. Because nitriles are fairly non-reactive. If you want to make them react, you have to go to a little bit more brutal conditions. So it's not an oxidation, right? Because carbon's got 3 bonds to nitrogen. Here it's got 3 bonds to oxygen. So it's bonded to something more electronegative than itself already. So you're not increasing the number of bonds from carbon to something more electronegative than itself. So it's not an oxidation. It's easy to predict the product though. You're just going to cleave that triple bond, and the nitrogen is going to come off as ammonia, and then that carbon is going to it's going to convert, not oxidize, right, to a carboxylic acid. So the mechanism is pretty involved. If we go through the mechanism, how this works. So since you're an acid, you can protonate the nitrogen, and then a water molecule can attack this carbon, and then let's break the double bond, break the triple bond. So put a lone pair on nitrogen. So that would take you to here. And then let's lose a proton from the oxygen. So lose H+, those 2 electrons become a lone pair on oxygen. And then we're going to take the lone pair on nitrogen, protonate it again. So basically you're going to kind of repeat these steps. It's a bunch of protonation, deprotonation steps. So protonate the nitrogen, and then we're going to take a lone pair on oxygen, make a carbon oxygen double bond, and those electrons become a lone pair on nitrogen. And then the second oxygen comes in, so another water molecule comes in, and break the double bond that you just made. Okay, so now lose a hydrogen on the water molecule that just came in. Okay, so getting closer. So now we're going to protonate the nitrogen again. So now you've got your NH3. And so we're going to remake a carbon oxygen double bond and lose a molecule of ammonia. And then last step, lose the hydrogen from oxygen. And now you've got the carboxylic acid and you have the ammonia side product. All right, so the mechanism's pretty detailed. Predicting the product is easy, right? If you have a, so how do you make nitriles? If you remember, you can do them by SN2 because CN- is a really good nucleophile. So cyanide's a good nucleophile. So it can come in and kick off a leaving group, whether that's chlorine, bromine, iodine, or a tosylate. And then once you have the nitrile, if you recognize the recipe, a nitrile, acid, water, and heat is just going to cleave that triple bond. That carbon would become a carboxylic acid, and the nitrogen will come off as ammonia. Okay, so there's several other ways to make carboxylic acids. You can make them from acid chlorides. You can make them from anhydrides. You can make them from esters. You can make them from amides, all through acid hydrolysis, and we just looked at nitriles. So they're all similar mechanisms, and all these 5 acid chlorides, anhydrides, esters, amides, and nitriles are what are called derivatives of carboxylic acids. That means if you react them with water, you get a carboxylic acid out, and that's what the next chapter covers. So basically in each case, you have a water molecule that attacks the carbon. Here you lose a Cl. Here it attacks there. There you would lose a carboxylic acid as a leaving group, or if a water molecule attacks an ester, then you would lose an OR group as it would ultimately come off as an alcohol. Or if it's an amide, then water comes in here. We'll look at the mechanism in the next chapter. Then you would kick off the amine, and in this case, of course, 2 water molecules that have to come in here, and then ultimately that it comes off as ammonia. So all of those 5 derivatives reacting with water, and whether you need acid and heat or not depends on the reactivity. And we'll talk about that more in the next chapter. But they all give, since they all have the same carbon structure, they would all give the same carboxylic acid. They just have different leaving groups, right? HCl or carboxylic acid or alcohol or amine or ammonia. Okay, we'll stop there.